Alright, Math 3, functions and their inverses 1.4. So these first ones are kind of a review about the properties of exponents. Remember, when you're multiplying with the same base, like 3 and 3, you add the exponents. So 3 to the 6th times 3 to the 5th would be 3 to the 11th. Because remember, exponents is just repeated multiplication, so it's like you have 6 3's being multiplied together. And here you have 6 5's being multiplied together, and those are all being multiplied together. So we end up with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 3 to the 11th. Okay? So now if we look at this, we've got 2 and 2, so we add the 3 and the 7 to get 2 to the 10th. Okay, and that's all we wanted to do. We didn't want to make it any different than that. Okay, now 7 and 7. 2 and 6, so it would be 7 to the 8th. Okay, next one, number 4, 10 to the negative 4, 10 to the 7th. Okay, well, there's two ways you can approach this. The easiest way would just be going negative 4 plus 7. Negative 4 plus 7 is 3, so it would be 10 to the 3rd. The other thing to remember is that a negative exponent actually makes it a fraction. So instead of 10 to the 4th, it'd be like 1 over 10 to the 4th. Times 10 to the 7th. And then you'd end up with 10 to the 7th over 10 to the 4th. And then the rule with the quotient rule is that you subtract them. So it would be 7 minus 4, which would still get us to 10 cubed. Okay, number 5, same idea. It would be 5 to the 3rd. 9 minus 6 is 3. For number 6, p squared, p to the 5th would become p to the 7th. Doesn't matter if you have numbers or letters. You'd end up with the same thing. Okay, number 7, 2 to the 6th times 2 to the negative 3rd times 2 to the 1st, because if it doesn't have an exponent, it's 1. 6 plus a negative 3 would be 3, plus 1 would be 2 to the 4th. Number 8, b to the 11th times b to the negative 5 would be b to the 6th, because 11 plus a negative 5 would give us 6. Okay, number 9, these ones now with the quotient rule, okay, we just go the exponents subtracted. Just like multiplication, we're adding the exponents. With division, we're subtracting. So it'd be 7 to the 3rd. Number 10, that'd be like 9 to the 1st. So it'd be 9 to the 7th. 8 minus 1 is 7. 3 to the 5th over 3 to the 8th would give us 3 to the negative 3, which would be 1 over 3 cubed, which it wants positive exponents, so you need to leave it in the fraction form. 13, when you have a negative up top, you can either drop it down, or we could subtract negative 3 minus 5 would give us p to the negative 8, which would be 1 over p to the 8th. Or you can think of it this way, this negative would make it 1 over p to the 5th, p to the 3rd, which we would combine those to become p to the 8th. Okay, now that last one, number 14, we'd go 7 minus a negative 4, which would be like plus, so it would be x to the 11th. Or you could think of it like this negative on the bottom would bump it up to the top, and you'd have x to the 7th times x to the positive 4. Okay, so there's those ones. Okay, now 15, it says, given the function f of x equals square root of x minus 1 and g of x equals x squared plus 7, first let's calculate these numbers. Okay, so f of 16, we would just put 16 in for x, so square root of 16 minus 1, square root of 16 would give us 4, 4 minus 1 would give us 3. B says write it as an ordered pair. So f of 16 equals 3, which is an ordered pair. 16 would be the input, 3 would be the output. Okay. Then for g, we have g of 3, right? G of 3 equals 3 squared plus 7. 3 squared is 9. 9 plus 7 would give us 16. So g of 3 equals 16. So that would be 3 for the input, 16 for the output. Okay. Now, what do the ordered pairs for f of 16 and f of 3 mean? Notice that they've just switched the inputs and outputs. When we switch the inputs and outputs, we are then referring to inverses. It would imply that these two functions are inverses. Okay, now let's do it with f of 25. So if I do the same thing but with 25 instead, let's see what we get. So square root of 25 is 5, minus 1 would give us 4. So f of 25 would be 4. Okay. So based on this answer, if these are inverses, g of 4 would probably be 25, wouldn't it? But let's double check. So let's put a 4 in here instead of a 3. So 4 squared is 16. 16 plus 7 is 23. Did they match? No. So are they inverse functions? No, because they would have to work the whole time. Just because they work in one instance doesn't mean that they're going to work the whole time. Okay? Alright, now let's actually match up some functions with their inverses. Easiest way to do this is just find the inverse. So remember, to do that, make the f of x y, then we swap the x and the y, and we simplify. Well, by simplify, solve for y. So we subtract by 5 to get x minus 5 equals 3y. Divide everything by 3. We get x minus 5 over 3 equals y. Which then we could change that to our inverse function, right? So that would be this one right there. So for 16 we would get C. Okay, then we do it for 17. So change that to x, make that y. It's kind of a shortcut. Well, what's the opposite of taking something to the 5th power? It would be the 5th root. So we'd end up with the 5th root of x equals y. Or the inverse. So we'd end up with the 5th root of x for g. Next up we look at 18. So I'd go y equals the 5th root of x minus 3. We swap them out, so x equals the 5th root of y minus 3. So we'd take it to the 5th power. X to the 5th would equal y minus 3. Add 3 to both sides. We'd get x to the 5th plus 3 for our inverse. So it would be f. So number 18 would be f. Alright, so number 19. We would go y equals x cubed. Then we'd swap it, x equals y cubed. Take the cube root, and we get the cube root of x equals y, or the inverse. Okay, so the cube root of x would be b. So for 19 we'd have b. So 20, f of x equals 5 to the x. Okay, let's skip that one for now. Because we would make it y equals 5 to the x. We'd switch it, x equals 5 to the y. Well, how do we take the y root of something? Okay, so let's see what that ends up matching up with when we get the rest done. So 21. So we go y equals 3 times x plus 5. So we would swap the x and the y. And then we would solve. So divide by 3. So I'd get x over 3 equals, because those would cancel, y plus 5. Subtract 5. Get x over 3 minus 5 equals y, which would be D. Okay, and 22, 3 to the x. Okay, now notice we've eliminated all of these but a and e. Notice that we have 5 to the x, that one has 5. 3 to the x, 3. So that would be a, and that would be e. Okay? Alright, now let's figure out how to double check if something's inverses. Okay, so we could do it multiple ways. We could just take this, find its inverse, see if it matches up. That would be a perfectly reasonable way to do it. I'm going to do it using function composition, which is this guy, where I would go, first off, I'd go f of g of x, which means I would take this f function and put the g inside of it for x. So I'd go 2 times g of x, which is x minus 5 over 2 plus 5. Then we simplify. That cancels out. X minus 5 plus 5 becomes 0. We're left with x. That's a good sign. And we do it the opposite way. So I go g of f of x equals, now I go x minus 5 over 2, but instead of x, I put 2x plus 5, then minus 5. That's like the whole x piece over 2. Positive 5 minus 5, that's 0. So I get 2x over 2. That cancels to x. So yes, 23 are functions. So we'd say yes, they are after showing all that work, because it wants us to show the work as well as do it. Okay, 24. We do the same thing. So I'd go f of g of x equals cube root of x minus 2 plus 2 cubed, because that x represents this. This becomes 0. Cube root of x cubed undoes each other, and we end up with x. Okay, then we do it the opposite way, so I go g of f of x. So I'd go the cube root of that whole thing, x plus 2 cubed, then minus 2. Cubing a cube undoes it, so we get x plus 2 minus 2. That becomes 0, so we're left with x. So 24 works as well, just like that. So these two were functions because of how they ended up. Okay, take this, plug it inside for x, so I go 3/4 times 4 times x minus 6 over 3 plus 6. 3 on top, 3 on bottom, 4 on bottom, 4 on top, they cancel. We're left with x minus 6 over 1, which is just x minus 6 plus 6. We end up with x. Then we do the g of x one, so I'd go 4 times 3/4 x plus 6 minus 6 over 3. That becomes 0, so I eliminate it. 3/4 times 4, those cancel. We're left with just 3x over 3. Those cancel. We're left with x. So that's what it would look like, and yes, those would be inverses as well. Alright, let's look at 26 now. So same idea. So I take this, so negative 3 over that whole thing, negative 3 x minus 2 plus 2. Now, so that's like negative 3 divided by negative 3 over x minus 2. So I can't divide by a fraction, so we multiply by the reciprocal. So times x minus 2 over negative 3. Those eliminate, and we're left with x minus 2 left over, plus 2 becomes 0. So x plus 0 is just x. Now, going the other way, g of f of x would go negative 3 over x plus 2 minus 2. That would become 0, so we get rid of that. Then we'd have negative 3 divided by negative 3 over x. But we can't divide by a fraction, so we multiply by the reciprocal. So times by x over negative 3, those cancel. We're left with x. So all of them are showing inverses, and that's how we check. That's one way. You could have also just taken one and found its inverse to find the others. That's, that really does work for that as well. Okay, now it says, let's pair up these with their graphs. So, if we recall, these ones, fractions with x's on the bottom, those are rational. Rationals look like a. So a would be number 26. Okay. If we look at b, it's linear. D is also linear. C is not linear. Okay. If we look at 23, linear. 25, linear. So 24 has to be the not linear one. So that's graph 24. So B and D. Okay, how are we going to check these ones? Well, let's try y-intercepts. So that y-intercept would be negative 1, 2, 3, 4, 5, 6, 7, 8. Negative 8. And this y-intercept would be 1, 2, 3, 4, 5, 6. 6. So do we see a y-intercept with a positive 6? Yes. Would that also have a negative 8 over here? It could, because if we went 4 times x minus 24 all over 3, be 4/3 x minus 8. So yeah, if we simplified it, it would. So 25 is going to be B, which means 23 would be D. Okay. Now it says graph the line y equals x for each of those. Okay, the graph of y equals x looks something like that. Okay, now it says, what do you notice? Hopefully something we talked about, this y equals x, is a line of reflection. So the graph and its inverse are the same thing across if we folded it. Okay. Do you think your observations about the graphs in number 27 has anything to do with the answers you got when you found f of g of x and g of f of x? Yeah. When we put the function in, we ended up with x as the answer, right? Well, y equals x is that line. So, yeah, there was a connection there, wasn't there? Okay. 29 says, look at graph B. Shade the two triangles made by the y-axis, x-axis, and each line. What is interesting about these two triangles? So, B. So, let me graph this. So, it says, by the x-axis, y-axis, and each line. Oh, I see what you're saying. This triangle. And that triangle. Okay, what do we notice about them? Look at that line again. Well, they're reflections of each other again. Okay. What about if we did it for D? They would still be reflections of each other? I would say, yeah, they're interesting in the same way. And I think that is it, so we'll call that good.